All right, welcome back. So let's talk some more about calculations using capacitors. The first thing I want to do is talk about the engineering of capacitors. So in a circuit, we use the symbol with two parallel lines connected by wires. Whenever you see that symbol in a circuit diagram, it means a capacitor. So if we're going to calculate the capacitance in farads of a physical object, I'm engineering a new capacitor. The calculation is this. Now let's talk about what each of those variables is. We mentioned that the plates had to have a lot of surface area. So this is the area of one plate, understanding that it's mirrored by the opposite plate. And this is in meters squared. So if I have a big sheet of metal, measure its square meter area, that's what I'm going to use in my capacitor equation. D is the distance between plates. This is also listed in meters. Now, in an actual physical capacitor, it may be millimeters or micrometers. But that's the distance between the plates. Epsilon 0 is a constant. It is given as a reference number. It'll always be on the exam given. It's equal to 8.85 times 10 to the negative 12 coulombs squared per Newton meters squared. Okay, so that's the same number in every calculation. And this last number, kappa, is the dielectric constant. For the separator material. And it's based on how polarizable that material is. And kappa for air is equal to 1. Okay. Kappa for example, Teflon is equal to 2.1. And paper is equal to 3.7. There are some capacitors that use oil or other polarizable liquids. The point is to have a material that can be polarized to help you get those plates closer together without touching, but we don't want to be able to conduct electricity. And so in some capacitors, they actually use water, but it's got to be super purified water so there's no ions that can conduct electricity between the plates. So kappa is either what you're solving for, or it is given in the problem. Okay? So the idea is, if I stick a sheet of paper between the two plates, I can get them as close together as the thickness of the paper, right? And if I can get them close together, I can store up more charge. Because the closer you can get those two materials, the more charge you can store in a capacitor. So from an engineering perspective, being able to get those plates as close as possible is important. There's another, so that's enough information to calculate how much capacitance your capacitor has. The other engineering factor that is important is the dielectric breakdown. Okay, and we've all experienced dielectric breakdown when you scuff your feet across the carpet and then you reach out to touch the wall and you strike a spark between your finger and the wall. That's when you have achieved dielectric breakdown of the air in between your finger and the wall, and you strike a spark that conducts electricity and moves charges from one to the other instead of maintaining separate charges, which is what gives you static electricity. So for air, the dielectric breakdown is 3 times 10 to the 6th volts per meter. Now that's a lot, right? 3 million volts per meter. So that means if I stand here with my finger 1 meter away from the wall, if I'm 1 meter away, it would take 3 million volts worth of potential energy difference between my hand and the wall to ionize the air in between. But a meter is huge, right? You don't get a spark from the wall until you're maybe millimeters from the wall, right? If I'm a millimeter from the wall, it only takes 3,000 volts. If I'm a micrometer away from the wall, it takes 300 volts, okay? I'm sorry, that takes 3 volts if I'm a micrometer away. So dielectric breakdown is dependent on how close those two surfaces are, as well as the voltage that they're trying to separate from one another. For Teflon, it's 60 times 10 to the 6 volts per meter. So an advantage of using Teflon, there's 2 advantages. Number 1, I can get twice as much capacitance for the same separation. And it's going to be, I can get those plates 20 times closer before it fries my circuit. So that's a good deal, right? Paper is 16 times 10 to the 6th. And there's lots of, these are just 3 pieces that I pulled off of the tables that are in the chapter. They're not particularly special. There's a lot of paper separated capacitors, but there's also a lot of other more effective materials that are used as well. Okay, so we're not only worried about how much we can store, but how easy it is to break it, really. And so that becomes an issue. So once you pop all the numbers in, you get farads out. Okay, so say that I want to put a capacitor into a circuit, and I want to calculate what's going on. So if I take, I'm going to create a circuit with one electrical element other than the power source. Okay. So this is a very simple circuit. In this part of the circuit, this is a capacitor, which is connected by wires to 2 ends of a battery. Okay. And on a battery, you might see one short long symbol or you might see 2 or 3 or 4 short long symbols in a row. Those are the cells in the battery. So for example, if I put 3 AAA batteries in a row into my calculator, I might use 3 single cell symbols in a row to symbolize that this is 3 AAA batteries and this is 1 AAA battery. Okay, so that's a symbol that comes from applications. But there's a short and a long. The long side is always the plus side. So sometimes I like to add a symbol, add a cross across the top one to remind myself that this is the positive side and the other side is the negative side of the battery. Okay, and what we have in a circuit is electrically we talk about positive charges flowing, and that's not true. It's a good visualization. What is true is that the electrons flow. But most of electrical understanding arrived before we knew about electrons and protons. So they just talk about the positive flow. So the positive charges flow around the circuit and they pile up on the capacitor, on one plate, the close plate of the capacitor. Once those charges are deposited on that plate, it attracts negative charges. So positives on one plate attract an equal number of negatives for the other side. And that's a charged up capacitor. And that circuit is what we use our Q equals VC on. So if I put a 9-volt battery, Q is not volts. V is volts. Here we go. 9-volt battery onto a 10 microfarad capacitor, I get 90 microcoulombs of charge stored. Okay, if I only put a 6-volt battery on there, I would only get 60 microcoulombs stored. So we're using the voltage difference to push charges into the capacitor. And we think about voltage on those electric field lines. Remember, we had our equipotential lines where the top of the hill had the highest voltage and you come down to lower and lower voltages. Voltage is like a hill, right? A 9-volt battery is a really tall hill, and we're using the pressure from that voltage to push those charges onto the capacitor because charges don't like to be crammed into a small space, right? They repel each other. But the more push I use, the more pressure from the hose into the water balloon, the more I can force into that water balloon against the force of the rubber trying to retract. So in a circuit, this is how we set up a diagram that shows us the capacitor that we're working with. Okay. The next video is also part of this series, and we're going to talk about using several capacitors in different kinds of circuits. So see you soon.